So, good evening, all of you. I'm Subhabrata Barman from the Assistant Professor from the Department of Computer Science Engineering at the Institute of Technology. So today my lecture topic is AI in chess. So this is basically a part of artificial intelligence course. And this course is actually studied in the undergraduate curriculum. And so we all know that game theory or game theoretic search is a topic in AI, and we try to discuss over here how what are the AI techniques in the AI techniques which are applied in game theory, or what are the search techniques which are employed in game theory. So we shall discuss about the AI techniques or the AI search techniques, the game theoretic search techniques in chess game. So now let us talk about the history of computer chess. So in 1951, computer scientist Alan Turing he develops the first program on pen and paper, which was capable of playing a full game of chess. In 1968, international grandmaster David Levy made a famous bet that no computer would be able to beat him within another 10 years. So he won his bet in 1978 by beating the computer chess game Chess 4.7, which was the strongest game at that time. So he acknowledged then that it would not be long before he would be surpassed by any computer program. So in 1989, Levy was defeated by the computer program Deep Thought in an exhibition match. However, chess computers could not still defeat the chess grandmasters and the world champions. So in 1996, the first computer to defeat the then world chess grandmaster was Deep Blue, which was developed by IBM, and the chess grandmaster, the computer program Deep Blue, that was developed in 1996, defeated the world champion Garry Kasparov. However, Kasparov won the series by 4-2. 1 year later, Deep Blue actually defeated Kasparov by 3.5, 2.5. So current machines are far ahead. Okay, so current machines are actually high performance computing systems that run these programs. Now, let us talk about what is a zero-sum game. Let us talk about what is a zero-sum game. So basically, the total gains, the total payoff, positive or negative, of the participants added up at any instant of the game sum to zero. I am on the 15th slide. Okay, so what is a zero-sum game? So the total gains, positive and negative, the total payoffs of the participants added up at any instant of the game sum to zero. That is called zero-sum game. So any result of a zero-sum game is zero-sum situation is a Pareto optimal situation. So some examples of zero-sum games are the chess game, the tic-tac-toe game, the checkers game. Strategies such as the min-max algorithm are used to maximize the gain or maximize the payoff from a zero-sum game. So minimax, sometimes minimax or sometimes known as min-max, is a decision rule used in game theory for maximizing or minimizing the possible loss or gain for a worst case scenario. So the theory behind minimax is that the algorithm's opponent will be trying to minimize whatever payoff or whatever value the algorithm is trying to maximize, hence minimax. So the computer should make the move which leaves its opponent capable of doing the least damage. Okay, so the minimax algorithm is a recursive algorithm for choosing the next move in an n-player game, usually a two-player game. So a value is associated with each position or state of the game. So this value is computed by means of a position evaluation function, and it indicates how good it would be for a player to reach that position. Okay, so the player that makes the move, the player then makes the move that maximizes the minimum value of the position resulting from the opponent's possible moves. Okay, so we label each level of the search space or the search tree according to the move. So starting at the leaf nodes, we label each leaf node with a positive, with a +1 or a -1 or 0, okay, or +1 or 0, depending upon whether it is a win for max. So if it is a win for max, the payoff is labeled as 1, +1, or if it is a win for min, it is labeled as -1, or sometimes it is labeled as, different conventions are used actually, so it can be 0 or it can be -1. So now what we do is we evaluate the payoffs at the leaf nodes, and then what we do is we propagate the payoffs or the position estimation values, okay, upwards. So if the parent is max, we give the maximum value of its children. Okay, and if the parent state is mean, we give it the minimum value of its children. So this is the search tree actually for the min-max algorithm. You can see that these are the leaf nodes and these are the payoffs or the utility values which are actually evaluated at the leaf nodes. And what we do is we propagate these values upwards actually. So say these are the min nodes, and at the previous level these are the max nodes, and then again the min nodes, and then the max nodes, and so on. So we start with the game starts with the min nodes, and then we have the max nodes, then we have the min nodes, then the max and min nodes alternatively. So what we do is we actually propagate these values actually upwards. So if these are the min nodes, these are the mean nodes, so we propagate the minimum value of its children. Okay, you can see we propagate the minimum value of its children at the previous level, and then these are the max nodes, so we propagate the maximum value of its children at the previous level. Okay, so In this way, the minimax algorithm works. Okay, so we propagate the value up to the root. Okay, so now what the thing is that we have something called pruning. Okay, so we have a pruning technique which is known as alpha beta pruning. There are various other pruning techniques. We have shallow pruning, we have deep pruning. So we have here, we present an alpha beta pruning technique, so which is a pruning technique or pruning algorithm which seeks to decrease the number of nodes that are evaluated by the min-max algorithm. So this decrease is required because we want to reduce the complexity of search. Okay, so what it does, how it prunes is that it stops completely evaluating a move when at least one possibility has been found that proves that the move is said to be worse, or it proves to be worse than the previously examined position. So when this rule is applied to a standard minimax tree, it returns the same move as minimax mode, but it prunes away the branches, it cuts down the branches of the tree that cannot possibly influence the final decision. Okay, so let's try to understand in a better way. So alpha beta search proceeds in a depth first fashion. So an alpha value is associated with a max node, which is an initial value or a temporary value which is assigned to a max node, because max nodes are given the maximum value of its children. So the alpha value can only go up, and we have a beta value which is an initial value or a temporary value which is associated with the min node, because min nodes are given the minimum value of its children. So beta value can never increase, it can only go down. So now the alpha pruning is done at the max node and the beta pruning is done at the min node. Okay, so for example, suppose a max node's alpha value is equal to 6, then the search needn't consider any branches emanating from the min descendant that has a beta value that is less than or equal to 6. So if you know the max node has its alpha value of 6, and it can only increase, cannot go down, you know that one of its min descendants has a beta value which is less than or equal to 6, and you need not search any further below the min node. So essentially a search can be stopped below any min node that has a beta value less than or equal to the alpha value of its max ancestors. Okay, so this is a diagram by which the alpha pruning is actually elaborated. Okay, so you can see the max node, this is the max node, these are the min nodes, and this is the max node. Okay, and min nodes alternatively. So you can see that since these are the we actually propagate the minimum value of its children. Okay, so here we propagate again in the next level, we propagate the maximum value of its children, and here we actually prune the branches. These branches actually are pruned. So this is alpha pruning actually. So basically if the max node, so basically this is the max node. The max node, if the max node has an alpha value of 5 or 6, you need not consider searching any branches emanating from the min node that has a beta value which is less than or equal to, its alpha value. Okay, so we actually prune the nodes, prune the branches here. So beta pruning is analogous to alpha pruning on the min node. So if a min node's beta value is actually 6, we need not search any further below a descendant max node that has acquired an alpha value of 6 or more. So beta value can only go down, can never increase, can decrease. So therefore, for beta pruning, search can be stopped below max node that has an alpha value which is greater than or equal to its equal to the beta value of its mean ancestors. Okay, so we can see the alpha and beta pruning in action. So this is the max node. So this is the player A's turn, and we get the max value of the next moves. And this is at the next level we have the player B's turn. So these are the mean nodes. So we try to get the mean of the next moves. Then again player A's turn, and then player B's turn, and these are the leaf nodes actually. So we actually evaluate the first. We need to evaluate the payoffs or the utility values at the leaf nodes, and then we need to propagate these utility values upwards, depending upon whether it is a min node or a max node. Okay, and thereafter we need to do the pruning. Okay, according to the alpha pruning rule and the beta pruning rule. And here, actually, these nodes, these green nodes, actually decide or they can determine that which of the states that these states in pink can be pruned. Okay, so now there is something called iterative deepening. So iterative deepening means it repeatedly calls this fixed depth search routine with an increasing depth in an iterative manner until a time limit or a depth limit is actually reached. So with a high probability, good move in a dth iteration is also a good move in the d plus 1th iteration. So it repeatedly calls a fixed depth search routine, and we gradually increase the depth. Okay, so we can order our search using this knowledge to obtain a greater degree of alpha beta pruning. Okay, so it is much faster since it prunes better. So basically, if we want to make the program to a fixed time to play, we can set the response time so that, for example, in the end game, where the possibilities are less, the algorithm can search to a greater depth, whereas in the start game, it would search for a smaller depth. So if transposition tables are used, we'll discuss about what is a transposition table. Then many position evaluations and the best moves can be stored in the transposition table. The depth search trees can have a better move ordering than starting immediately searching at deep level. So a transposition, what is a transposition table? A transposition table is essentially a hash table that stores the scores of the previously searched positions in the game tree. So when we are designing this computer chess game, we actually use this transposition table. This improves iterative deepening since we simply have to look up certain positions instead of expanding them to find the score. We also use a Zobrist hashing technique, which is used to store the scores of the different positions of the chessboard in the transposition table. So a transposition table contains a hash score or a hash value. So this is basically the Zobrist hash representing the chess position. We also have a depth. So the depth remaining in the alpha beta search. So a depth of 5 would mean that the score is recorded for a 5-ply search. Then we have a score, which is the evaluation score for the particular position of the game. Then we have a field called ancient. So this is basically a Boolean type of field. Okay, so it's a Boolean flag. So if false, the node will be replaced by a newer entry. And we also have a field called node type. in the transposition table. So there are three types of nodes. We have the exact node, the alpha node, and the beta node. So exact means this node represents the exact score for the tree. However, in the events that in events of alpha beta cutoffs, we can't use the score as an exact score. An alpha node type means the value of the node was at most equal to the score. The beta node type means the value is at least is the least value equal to the score. So Zobrist hashing starts by randomly generating bit strings for each possible element of a board game. For example, in chess, each of the 64 squares at any point of time can be empty, or it can contain one of the 6 game pieces, which are either black or white. So each square can be of 1 plus 6 into 2 is equal to 13 possible states at any point of time. So the position of the board can be updated simply by zoring out the bit strings for the states which have changed and zoring in the bit strings for the new states. So if a pawn on the chessboard square is replaced by a rook from another square, the resulting position would be produced by zoring the existing hash with the bit strings. For zoring the existing hash with the bit strings for a pawn at the square, zoring out the pawn at the square, a rook at the square, zoring in the rook at the square, and the rook at the source square, zoring the rook at the source square, or nothing at this source square, zoring in the nothing at the source square. Now there are different modifications and improvements on the min-max search algorithm. There are 3 modifications. We have the aspiration search, then we have killer heuristics, and we have opening and end-game databases. So the min-max algorithm requires a value to be associated with each position of the chessboard. The value must reflect the strength or the goodness or the fitness of the player's position in the game. If the player is winning, the associated value will be positive. If the player is losing, the associated value will be negative or 0. Okay, so things to be considered in heuristic. Heuristics are used to evaluate certain situations, thumb rules basically. So, which are the things if we use heuristics in this chess game. So, what are the things that are considered to be considered in heuristic? In designing a heuristic function, we should consider the material advantage. We should consider the positions of pieces. Okay, so material advantage is queen is worth 9 pawns, rook is worth 5 pawns, and bishops and knights is worth 3 pawns. And the king is actually priceless, because if you lose the king, you lose the game. So positions of the pieces, freedom of movement. Bishops are more dangerous when they are positioned on an open diagonal. Similarly, open columns and ranks are useful places to keep your rook. Safety of the king and pawn. So these are the things that you should be considering while designing your heuristic function. Okay, so this is an interesting situation on the chessboard. So in 2002, Vladimir Kramnik played 8 games against Deep Fritz, the computer chess game Deep Fritz. So Kramnik won 2 games and 3 by conventional anti-computer tactics, play conservatively for a long-term advantage. The computer is not able to visualize this in the game search tree. In 1997, Garry Kasparov played an unusual opening. So these are some of the anti-computer techniques which are used to defeat the computer. Okay, to cheat the computer. But chess computers' unwillingness to accept 50 move draws when it has a solid material advantage, can be exploited. Okay, so with that we come to the end of this lecture. We have used some references from Wikipedia and the www.chessprogramming.com. There are other web resources, bibliographies. So these are the bibliographies that we have used for our lecture. Thank you.